Very pleased to be here today. I'd like to thank Kevin and Charlie for inviting me, for the warm welcome. And I'd like to talk to you today about the new astronomy of LIGO. So before I can do that, I basically have to answer a question, which is, what is LIGO? Some of you may have heard of LIGO, others of you may be going, well, what is LIGO? So I'm going to walk you through what LIGO is. I'm going to go through, LIGO is an acronym. What it stands for is, the first part stands for the Laser Interferometer, Gravitational-wave, Observatory. That's basically the outline of my talk. So what I'm first going to talk about is, I'm actually going to do it slightly out of order. I'm first going to talk about gravitational waves. And I'll tell you about LIGO, about this new kind of astronomy. I have to tell you what gravitational waves are. And so I'm going to introduce gravitational waves, say where they come from, say what they are, how they might relate to things we're familiar with in our everyday experience, because gravitational waves are certainly not something we experience every day. Then I'm going to tell you about laser interferometers, which is the tool we use for detecting these gravitational waves. And finally, since LIGO, the goal of LIGO is an astronomical observatory to observe the universe, to learn more about the universe, to study astrophysical processes, study phenomena, see deep into the universe, and even through the thick cloud layer that constantly surrounds Syracuse, see exactly what's going out there. I'm going to tell you about the sources we're looking at. So I'm going to tell you about what we're trying to observe with LIGO. Then I'll conclude with what the status of LIGO is right now, and where we're going in the very near future, and looking over the horizon to the next generation. Okay. So let me start with gravitational waves. Let me tell you about gravitational waves. Before I do that, I want to take a step back and talk about something that people are probably much more familiar with, which is electromagnetic waves. So there's electromagnetic waves in this room, there's light, you can see me using light, there's infrared radiation, because hopefully we're all warm, so we're emitting infrared radiation. Electromagnetic radiation is something we're very familiar with. We use cell phones to communicate, and pretty much so far, almost, and I say almost because there may be neutrino or cosmic ray people in the audience, but almost all of our knowledge of the universe comes from observing electromagnetic waves. Pretty much everything we know about the universe comes from observing electromagnetic waves. Light is the most obvious. People have been doing astronomy for thousands of years, looking up at the sky and saying, what's up there? People are doing astronomy with light, with visible light. So, visible light is a form of electromagnetic waves that we can use to observe the universe. Of course, it's not the end of the story. We have radio waves, we have X-rays. This is a picture of the Arecibo telescope, and this is the Chandra X-ray telescope. So, we have this whole palette of the electromagnetic spectrum with which we can observe the universe. We can observe with telescopes and do a better job than our eyes can alone. We can build giant radio dishes to observe the universe in radio waves, and if we go high above the atmosphere, up into space, where it's not shielded by the atmosphere from X-rays, we can build X-ray telescopes to observe very high-energy processes in the universe. So pretty much everything we know comes from observing electromagnetic radiation. We also know from many, many years of electromagnetic astronomy, dating back to the earliest times when people looked up at the stars, through Galileo's first telescopes, through the Hubble telescope, and now these new generations of telescopes that observe all the way across the electromagnetic spectrum, from X-rays over here, through the visible spectrum in the middle here, to longer wavelengths, to microwaves and radio. We know that when we observe the sky, when we observe the universe with different frequencies of the electromagnetic spectrum, we learn more about the things we're looking at. Take one source, take the Crab Nebula. This is a supernova remnant. This is a supernova that was observed about 1,000 years or so ago. If we observe it today, we see this remnant, which is the remains of a star that reached the end of its life, exhausted its fuel, and exploded, and created this beautiful nebula that you can see in the visible. This is a Hubble Space Telescope image of the Crab Nebula. You can observe it in the radio. You get different information. This is the same picture, this is the same source, taken in the radio, and you can see different structure here because the things in the nebula at different energies are emitting different electromagnetic frequencies. You zoom into the center of the nebula just here. You zoom into the center of this hot cloud of gas and observe in X-rays then with the Chandra Space Telescope, with the X-ray telescope, we can see this extremely energetic source. This is a false color image where we've taken the X-ray image and made it visible. We can see in the center of this nebula just here, there's this incredibly energetic luminous X-ray source, which is in fact a pulsar. It's a remnant of the star, a neutron star, the stellar remnant that's left over from this explosion, which you can't see in the visible light because it's emitting most strongly in the X-rays. So when we look at a single source with all these different electromagnetic frequencies, we learn much more about the universe. Okay, so that's electromagnetic. That's several thousand years of electromagnetic astronomy in a nutshell. What are gravitational waves? Well, gravitational waves date back to the early 19th century to Einstein. Einstein's theory of general relativity is our modern theory that tells us how gravity works. It's our picture of how gravity works. A lot of people are familiar perhaps with Newton's theory of gravity, the image of the apocryphal image of himself under the apple tree, watching the apple fall, and writing down Newton's theory of gravity. And that's been our classical picture of gravity for many, many years. You have two objects, have mass, there's a force of gravity between them, it's proportional to their masses, and inversely proportional to the distance. That's Newton's theory of gravity. Well, Einstein kind of stood everything on 10 and said, well, yeah, that's true in a certain limit of slow-moving things that aren't that massive, like planets and stars, small stars, but it's not the correct picture of gravity. The correct picture of gravity is general relativity. And I'll talk exactly what his picture, how we can look at Einstein's picture. In some ways, despite all the math here, Einstein's picture is actually a bit easier to understand than Newton's. To result to Newton's, I have to say F equals gmn over r squared. I can show you Einstein's theory of gravity in a nice little picture on the next slide. So, what is general relativity? What is Einstein's theory of general relativity? Well, Johnny Wheeler summed up all of Einstein's theory of general relativity, his theory of how matter and gravity interact, into one very nice, succinct sentence. And that is, in general relativity, matter tells space how to curve, and space tells matter how to move. What does that mean? Well, let's take a look at a picture. In Einstein's theory, space, the universe, space-time, the universe is like the surface of a trampoline. There's no matter around, the surface of the trampoline is flat. If you toss a bowling ball onto the trampoline is going to curve around the bowling ball. So the matter, the bowling ball, is causing the space-time of the trampoline to curve around it. And so the matter is telling space how to curve. My bowling ball and the trampoline is just an analogy. In Einstein's picture, the sun, for example, curves space around it. What does that look like in a little picture? So here's the normally invisible space-time. This is the space-time we live. We live in space-time right now. And my mass, the Earth's mass, is causing space-time to curve. This is the picture we think of. So we can think of it in a little two-dimensional picture. Imagine space, instead of being three-dimensional, to be a two-dimensional sheet. We drop the sun in the middle right here. Then what happens is the mass of the sun curves the space-time around it, just like when you drop a bowling ball on a trampoline, and it curves the trampoline. So matter tells space how to curve. Space tells matter how to move. What does that mean? Well, we go back to my empty trampoline. If I flick a marble across the surface of my flat trampoline, then the marble is just going to roll in a straight line across the trampoline. Okay? So, I'm sure people have done this, roll a marble across a trampoline, it's just going to go in a straight line. If you drop a bowling ball in the middle of the trampoline, and you flick a marble along the bowling ball, it'll see this curvature, and it'll get deflected around here, like this. And that's the curvature of space-time telling matter how to move. So, in Newton's picture, the Earth goes around the Sun because there's a force of gravity between the Earth and the Sun, and we have conservation of angular momentum and all this type of stuff. In Einstein's picture, what's happening is the sun is curving space-time, and the planets are just trying to go in straight lines. They're just trying to go in straight lines along in space-time. But they see the curvature of space-time around the sun, just like when you flick a marble across a trampoline, it'll curve around the curvature of the bowling ball, and that causes the Earth to go round and round the sun like this. So that's pretty much everything you need to know about Einstein's theory of general relativity. Matter tells space how to curve, and space tells matter how to move. Now, the solar system is not a particularly interesting place astronomically. If you want to look at the most violent events going on in the universe, you're not going to find them in the solar system. Fortunately for us, the solar system is a pretty staid, happy place. The Earth just keeps going around the sun. It sees the sun's curvature, goes round and round every year. The sun's burning its nuclear fuel, but it's not going to do anything dramatic on our lifetimes. So within the solar system, it's not a particularly dramatic place. But that's not true when you look out into the distant universe. There are incredibly violent astrophysical processes going on out there in the universe. And if you have massive objects moving around in space-time, moving around very, very fast, very, very massive objects, incredibly dense, some of the densest, most compact objects in the universe. In this picture, I've drawn two black holes going around each other. If you have two incredibly dense, massive objects going around each other very, very fast, then you don't have this nice staid curvature of space-time like we have around the sun. You have a much more dynamic, moving environment. You imagine dipping your hand in a tank of water and swirling your hand around. You're going to generate ripples. And those ripples are going to propagate outwards from the disturbance of you swirling your hand around in the center. Those ripples are going to propagate outwards to distances off out into the universe. Same thing happens in Einstein's theory of gravity. If you have two objects that generate gravitational fields moving around each other very, very fast, they're going to generate changing gravitational fields. So when massive objects move around, the curvature of space-time changes. And this changing gravity in the middle doesn't propagate out to every point in the universe instantaneously. It takes some time to propagate outwards. It propagates out at the speed of light. So information about these changing gravitational fields in here propagate out at the speed of light as ripples in space-time. Just like when you stick your hand in a tank of water, you swirl your hand around, and ripples on the tank propagate outwards on the surface of the water. So these black holes go around each other, or crash into each other, or stars explode. These ripples propagate outwards in space-time, carrying the information about what was going on in the middle. And it's these ripples in space-time that we call gravitational waves. For the physicists in the audience, just as theories that describe electromagnetism predict electromagnetic waves, when I turn on my cell phone, little charges move in the antenna of my cell phone, they generate electromagnetic waves. Einstein's theory predicts gravitational waves. When you change mass distributions around, you generate gravitational waves. And the thing that's really interesting for astronomy is not just that these things exist, but that these gravitational waves, just like the electromagnetic waves generated by my cell phone, carry information about the sources that generated them. The electromagnetic waves that my cell phone transmits encode the speech pattern of my voice. The gravitational waves that are generated by two black holes colliding into each other encode the information about that violent collision of two of the most astrophysically dense, extremely interesting objects we can see out there in the universe. So this is what gravitational waves are. And I can't emphasize enough that gravitational waves, they're not just a different frequency in the electromagnetic spectrum, they're not just a different wavelength in the electromagnetic spectrum. They're a completely different spectrum. It's like the difference between hearing and seeing. When we talk about electromagnetic astronomy, we talk about we're seeing the universe. When we talk about gravitational waves, it's like we're listening to the universe. You get a lot more information about the universe when you listen to it as well as looking at it. So gravitational waves are an entirely new way of observing the universe. And one thing that's really exciting about gravitational waves is if we can detect them, they bring a couple of big things. they give us insight into fundamental physics and astronomy. What do I mean by that? Well, fundamental physics, when we look at gravitational waves, we're looking at the nature of gravity. Einstein's probably the most famous physicist ever lived, right? And he's famous, GR is well, general relativity is well believed, everybody's heard of Albert Einstein. But believe it or not, Einstein's theory of relativity has only been tested in the limit of weak gravitational fields, because that's typically what we have access to. Solar system tests, weak lensing of light around galaxies. We've never tested GR in the regime where GR is really supposed to live, which is these incredibly strong gravitational fields, where it makes its most outlandish and outrageous predictions like black holes and gravitational waves. So we can observe these gravitational waves, then they give us insight into fundamental physics, and if we can detect them and decode the information that's encoded in these gravitational waves, we can use them to observe the universe and actually do astronomy. So, what is a gravitational wave? What does it do? So, I've told you what a gravitational wave is, but what does it actually do? So how do we need to understand something about the effect of gravitational waves in order to be able to detect them. Well, if a gravitational wave was to pass through the board right now, if I had a ring of particles just sat there, floating in empty space, imagine my screen here is just a blackness of empty space. If I had a ring of particles just sat there, as a gravitational wave goes through the board, the effect is to stretch and squeeze the distance between freely falling objects. We don't need to worry about what freely falling object means. What it basically means is if I was stood here, and the gravitational wave was to pass through me like this, it would stretch me in one direction as it squeezes me in the other direction, and then half the period of the wave later, it would stretch me in the other direction and squeeze me like this. And it's because gravitational waves, this is an effect that gravitational waves are a ripple in space-time. Space itself is being stretched and squeezed as the gravitational wave passes through and causes these distortions in space-time, carrying this information from distant sources. So you might ask, well, okay, if gravitational waves stretch and squeeze space-time, why aren't we constantly being stretched and squeezed and stretched and squeezed and stretched? Why don't we notice these things like every day? Why aren't they a nuisance, right? If everything in this room was just being stretched and squeezed all the time, it would be kind of annoying. But fortunately for us, in our everyday life, gravitational waves are very, very weak. We don't see the effect of gravitational waves on the scales that we're used to dealing with. So the stretching and squeezing of space-time happens at a tiny, tiny, tiny level. And I'll talk about how tiny in a few minutes. But gravity and matter actually couple much more weakly than electromagnetism and matter do. My cell phone can generate detect amounts of gravitational wave easily, but to detect amounts of gravitational waves is really hard. You need massive objects moving very fast, because gravity and matter couple very weakly. Gravitational waves are very, very weak. The problem with this is it's great for us because we're not being stretched and squeezed all the time, but it makes gravitational waves very hard to detect. You have to be able to detect tiny, tiny amounts of the stretching and squeezing of space-time, swamped out by all the other noise sources that are going on in everyday life. So if you have two particles and they're being stretched and squeezed together like this, you have to detect that stretching and squeezing above all the noise sources and vibrations and all the other stuff that just goes on in the world that makes things jiggle around, even just heat, the thermal motion of atoms are jiggling around because they're warm. All these things make it difficult to detect gravitational waves. So you might think, well, what's the point? Do we have any technology that can try and detect? Okay, maybe I've convinced you that the gravitational wave spectrum is really cool, right? There's a whole palette of things yet to be discovered in the spectrum that we've never used to observe the universe. But there's no point going on because you're never going to detect them. They're so weak. Now, how are you going to build anything that can detect these tiny, tiny ripples in space-time? Well, that's where laser interferometers come in. This is the technology that we can use to detect these tiny little ripples in space-time and use gravitational waves to observe the universe. So what is a laser interferometer? Well, first let me actually quantify what I said. Gravitational waves are tiny, but what does that mean? This next slide is going to have the only equations that are in my talk, but I just put them in to give you some sense of scale. I'll give you a better sense of scale in a second. The effect of gravitational waves is this stretching and squeezing, right? So you take a length and you stretch it and then you squeeze it. So let's say I have a meter stick and it gets stretched and it gets squeezed, then its length is going to change. The length between the two ends of the stick are going to change. And the strength of a gravitational wave is measured by the strain, right? Strain is the same thing you see in undergraduate lab. If you take an object, you stretch it, then there's some strain in there. Change in length divided by the length. Typical gravitational wave strains on Earth for astrophysical sources of gravitational waves, which are the only things that can really detect amounts of gravitational radiation, the strain, the change in length divided by the length, well, this is where Einstein's theory turns around and bites us, that this g over c to the fourth. G is the gravitational coupling constant, which is a very small number. C is the speed of light, which is a very big number. Take a small number divided by a big number to the fourth power, you get a really, really small number. This is what I mean by gravitational waves being so weak. This is the energy emitted in the gravitational waves, this is the distance. You get strains of order 10 to the minus 21. That's a pretty meaningless number, right? 10 to the minus 21. It's just 1, 0, followed by a whole lot of zeros, and then a 1. What does that actually mean? What can we actually get our heads around with that? Well, let's illustrate what 10 to the minus 20, a strain of 10 to the minus 21 is. We want to measure a strain of 10 to the minus 21 over a kilometer. What's that equivalent to doing? Well, my little cartoon here, here's the Earth. Here's Proxima Centauri, which is the nearest star to the Earth. Measuring gravitational wave strains on the surface of the Earth, measuring these changes in length of order 10 to the minus 20 or so meters, is equivalent to measuring the distance to the nearest star, which is 4.2 light years. You know the nearest star is a long way away. It's equivalent to measuring this distance to about 10 microns. This is really, really challenging. So in order to detect gravitational waves, you need to do the equivalent in displacement measurement of the distance between the Earth and the nearest star to a precision of 10 microns. Like measuring, with one of those little screw gauge micrometers. This is a really, really sensitive precision measurement. And again, you might think, well, can you even do this? The answer is yes. The technology we use to do it is one of these laser interferometers. It's a beautiful piece of technology. It's basically straight out of undergraduate labs. You can build one of these, maybe not sensitive enough to detect gravitational waves, but you can build one of these for about $50. Take a laser pointer, shine a laser pointer through a mirror, a half-silvered mirror, which we call a beam splitter. Half the laser beam goes up this way, hits another mirror up here, comes back down. Half the laser beam comes out here, hits a mirror, and comes back this way and recombines at the beam splitter. This is called a Michelson interferometer. Named after Michelson, the experiments he did were actually the foundation for Einstein's theory of relativity. Basically a tabletop piece of kit, shine the laser in here, hit the mirror, comes back, hits the mirror, comes back, and the light, when it recombines at the beam splitter, will actually constructively interfere in this direction, and all the light will head back towards the laser, and destructively interfere in this direction if the arms are exactly the same length, and no light will go to the photodiode. So if you set this up so the distance, this distance, is exactly the same as this distance, all the light will head back towards the laser, and none of the light will head towards the photodetector. This is the principle of a laser interferometer. Well, gravitational waves, when gravitational waves come through, they stretch and squeeze spacetime. So if a gravitational wave passed through this interferometer, it would stretch this arm as it squeezes this arm, and then half a cycle later would stretch this arm as it squeezes this arm, and upset this delicate balance between the lengths of the two arms. And now, instead of not seeing any light coming out of the photodetector, you'll start to see light leaking out of the photodetector and see these pretty little interference patterns coming out of the photodetector. So this laser interferometer is basically a very, very precise tool for measuring this length relative to this length. And if the lengths change relative to each other, then light starts to leak out. Gravitational waves will cause these lamps to change. Light will leak out. There's the signal encoded. The gravitational wave will be encoded in the light that comes out of this photodetector. Okay, so what do these things actually look like in practice? Well, in order to make a laser interferometer sensitive enough to detect these tiny, tiny displacement sensitivities from gravitational waves, you need to make really big laser interferometers. I said you can make one of these, a benchtop version, about $50. If you have an extra 300 million or so lying around, you can actually make one big enough to detect gravitational waves. This is what a laser interferometer that's big enough to detect gravitational waves actually looks like. This is not an artist's impression. This is a real picture. In fact, Amber's office is in here, so at least one person in this room has actually, three people in this room have actually been here and can prove it exists. This is the LIGO Livingston Observatory. What this is a 4-kilometer long laser interferometer with one of the most powerful continuous lasers. Inside this concrete this concrete shield here is a steel beam tube. That beam tube runs 2.5 miles from the beam splitter in here to a mirror at the other end here, and 2.5 miles or 4 kilometers out to a mirror over here. And the light comes back to the beam splitter and the photodetector and electronics in here. So one of the most powerful continuous lasers that's ever been, the most powerful and stable continuous lasers ever been developed is in this corner station. This is actually the world's biggest vacuum. Actually, the world's joint equal vacuum, because there's another one that's up at Hanford. And it's an incredibly sensitive precision piece of equipment for measuring the relative distance between a mirror here and a mirror here, relative to a mirror here and a mirror here. And as the gravitational wave travels through the observatory, it changes those lengths, and that length change, those gravitational wave signals, are imprinted on the light that's read out of the photodiode in here. The concrete beam tube here is to stop people from shooting at it. Because people go hunting in these woods and bullets go flying across here, and you don't want a bullet going through a beam tube that costs $300 million to make, and all the gas gets in, and that's the end of LIGO. So this is the LIGO Livingston Observatory. So we actually built a laser interferometer that can get down to these incredible sensitivities needed to detect gravitational waves. In fact, we didn't just build one, we built several. This is LIGO Livingston in Louisiana, and we built a twin observatory, the LIGO Hanford detector, up in Washington State. This is in southwestern Washington State. So LIGO Hanford, LIGO Livingston, together form the US LIGO Observatory. Why do we build two? Well, detecting gravitational waves is really hard. It's a tough endeavor. And I'll talk a bit more about in a minute about all the things that conspire to make this hard. Noise sources that are around, all these things that make it hard. We built two because if we detect a gravitational wave, it should pass through the Earth and be seen by both of these detectors. And if we see the same signal in both of the detectors, not only do we learn more information about that signal, but it gives us strong confidence that this really is a gravitational wave. Remember, if you're detecting a supernova, you can see the flash of the supernova. If you're detecting a gravitational wave, you're seeing these tiny ripples in space-time. We want to make absolutely sure we see them, so we built two of these detectors in order to be confident that we actually detect gravitational wave signals. We're not the only people who've done this in the US. The French-Italian Virgo collaboration has built a gravitational wave interferometer near Pisa in Italy. If you're given a choice to visit any of LIGO Livingston, LIGO Hanford, or Virgo, go to Virgo. Sorry. The fourth detector in the network is GEO 600. It's a 600-meter detector in Hanover, Germany. And these are kilometer-scale detectors. So LIGO is 4 kilometers long on each arm. Virgo is 3 kilometers long on each arm, just because they couldn't quite get 4 kilometers given the land constraints. GEO is 600 meters long. So LIGO and Virgo detectors are read in the astrophysics, but GEO is used to prototype advanced detector technology. So GEO makes a valuable contribution to the network by prototyping advanced detector technologies for the next generation detectors. So right now we have 4 detectors on 2 continents. We have The LIGO Hanford Observatory up here. You have LIGO Livingston down here. We have Virgo over here, and GEO up in northern Germany just here. The plan is to add, so we started with three LIGO detectors. There are actually 2 up here. We went down to 2, and now we're going back up to 3. I'll talk about that in a minute. But we really have basically a worldwide observatory. We have a worldwide network that's trying to detect these gravitational waves. With a worldwide network of 4 or more detectors, and there may be more detectors coming online. Japan is building a detector right now. They'll come online in a few years. The Australians are talking about collaborating with LIGO to build a detector. With all these observatories, we have a worldwide network that's poised to try and detect gravitational waves and use them to study the universe. It's important to have a worldwide network because we want to know, where in the sky are these gravitational waves coming from? We need to triangulate them. You can triangulate the location of submarines with different radio antennas that look for the radio signals. So we want to triangulate signals, we want to learn more from this worldwide observatory. Okay, so this brings me to observatory. What are we actually trying to observe? Talked about gravitational waves, but that's not where the real excitement is. The real excitement is in the sources of the gravitational waves. What's generating these gravitational waves? What are the astrophysical sources that we want to see with LIGO and its international partners? Well, there are 4 main sources of gravitational waves that we're considering right now. In fact, one of them is kind of a catch-all source for everything else. One source of gravitational waves is spinning neutron stars. One thing I didn't go into this talk because I didn't want to get too technical was exactly what types of, what configuration of masses you need to generate gravitational waves. But I can say it quickly in words, which is you need a spinning dumbbell. If you have just a sphere that's rotating, it won't generate gravitational waves. Just have a rotating sphere, it won't generate gravitational waves. You need some kind of dumbbell shape that's rotating. You need some kind of asymmetric shape that's spinning around and wobbling around, generating gravitational waves. And one of those sources is neutron stars. Something like the neutron star that's in the center of the Crab Nebula spinning around, and it might has a very strong magnetic field. That magnetic field might not be aligned with its axis of rotation, just like the Earth's magnetic field is not aligned with its axis of rotation. And it might have little mountains and bumps on it, and it wobbles around its axis as it spins around. So that neutron star spinning around, producing a continuous gravitational wave that just sounds like a sinusoidal tone that goes boo, is one of the sources of gravitational waves. Another source of gravitational waves is actually the Big Bang. This picture shows the cosmic microwave background, the electromagnetic waves left over from the Big Bang at the beginning of the universe. That Big Bang also created huge ripples in space-time that are propagating outwards, but by now have died off to just a gentle hiss of gravitational waves. We call these stochastic sources. This is the relic gravitational waves from the Big Bang. This is probably the most difficult source to detect because these days it's so weak, but it's also one of the most exciting because it let us see back to the first 10 to the minus 43 seconds after the beginning of the universe, way back to the earliest moments of creation. Our catch-all source is short bursts, things that go bump in the universe, things that collide, explode, just maybe things we've thought about like supernovae, exploding stars, they might generate gravitational waves. Or, unmodeled transients that we just haven't thought about. The final source, which is the one I actually spent some time on, it's the one we probably understand the best, is what we call, give the fancy name, compact binary coalescence. What this really means is 2 stars spiraling around each other, 2 stars orbiting each other, spinning round. You have this spinning dumbbell shape because the 2 stars are spinning around each other, emitting gravitational waves, spiraling in together as they emit gravitational waves. So I'm going to focus a little bit more on this because, like I said, this is A, it's the source I work on, so I have a bias, and B, it's probably the most likely the first source we'll find, and it's probably the one we understand the most. So each one of these could be a talk in of themselves, but for the remainder of the time, I'll talk about compact binary coalescence because black holes are cool. Okay. So what does compact binary coalescence actually look like? Well, this is a little cartoon showing what's going on with 2 black holes spiraling into each other. Black holes are curved space-time. Black holes are matter that's gotten so dense they basically become pure space-time curvature. So this is analogous to the diagram I showed earlier, where this is curved space-time around some massive object down here. And there's a smaller object going round and round and round this massive object just here. What does this look like in practice? Well, I found a great movie from the LIGO Livingston Business Center. I don't know if any of you have seen these spiral. Anyone seen these spiral wishing wells that you roll a coin down? So this is basically what happens when one of these small black holes or a small star rolls round and round the big central object in the middle. So this is a ball bearing. It's supposed to represent this small star going round and round and round in this curved space-time. This thing here, you can't see too well in the picture, but it's basically a black plastic funnel that looks like this. Watch what happens. So it's going round and round, and you can hear it going rrr. And as it goes round and round and round, the friction between the plastic sheet and the ball causes it to lose some energy of sound as it's going round. And it starts to spiral down and in. Gets louder and louder and louder as it goes down. Spinning around really, really fast. As it gets louder, it spirals in more quickly. Moving close to the speed of light. Until it goes to full. And falls down. And falls into the central black hole in the middle. This is basically, this little demo shows you exactly what happens with this thing we call, a fancy word, compact binary coalescence. It's a ball bearing going down a plug hole in space. So, what we're looking for, as these two stars orbit each other, there's no friction in space-time, but there's an analogous thing called radiation reaction. As these two stars spin around each other, they, just like this ball bearing is losing energy to sound, those stars lose energy to gravitational waves. The gravitational waves carry energy and information away from the system, and they spiral in together until eventually they crash into each other and merge. This is what we call compact binary coalescence, as the two binaries finally coalesce and go down the plug hole. So, what the real astrophysical sources look like? This is a cartoon. This is a ball bearing going down a plug hole. What types of things are we actually looking for? Well, one of the things we're looking for, we met a bit earlier in my talk, which is neutron stars. Neutron stars are a prime source of gravitational waves. We saw a picture of a neutron star from the Chandra telescope. This is a neutron star right here from the Crab Nebula. We know neutron stars exist because we've seen them with electromagnetic observatories. You can see neutron stars. So what is a neutron star? Well, take about 1.4 times the mass of the sun, and under its own gravity, compress it into a ball about the size of Manhattan, a few kilometers across. So the sun's really big, right? There's a lot of matter in the sun. Take 1.5 times the mass of the sun, compress it down to a ball, basically a giant atomic nucleus. A giant atomic nucleus containing about 1.5 times the mass of the sun in a ball a few kilometers across. That's a lot of matter in a really small space. If you can get that matter going around really, really fast, then you can actually start to generate gravitational waves that we can detect with LIGO. If you have two neutron stars orbiting around each other, so-called binary neutron stars, then you get gravitational waves. And we know that binary neutron stars exist because these neutron stars have incredibly strong magnetic fields, and they generate radio waves. This is where gravitational wave astronomy connects to electromagnetic astronomy, one of the many places. As these neutron stars spin around, we can see the flash of radio waves from their magnetic fields. Now, we know that binary neutron stars exist because we've seen them in the radio. We know they're out there in the universe. Like Hulse and Taylor won the Nobel Prize for observing the first binary neutron star. So we've seen their radio emissions. What we haven't yet seen, and what we're seeking with LIGO, is these gravitational wave emissions, the direct gravitational wave emissions that these neutron stars are emitting as they spin around each other. We know that these exist because we've seen them in the radio. We've also observed these things. We know where they are in the universe, and we can observe them in the radio for many years. We've observed a pair of binary neutron stars, the Hulse-Taylor pulsar, for about more than 25 years now. And we can see that it is actually getting closer and closer together. And it's getting closer and closer together and starting to speed up in exactly the way that Einstein predicts from gravitational radiation. So we have very good indirect evidence from radio observations that gravitational waves really exist. We can see this binary neutron star in the radio with radio observations, and we can see it's behaving in exactly the way that Einstein predicts it should if it's emitting energy in the form of gravitational waves. What we're trying to do with LIGO is to directly detect these gravitational waves and use the gravitational waves, well, A, to directly detect gravitational waves and verify a prediction of Einstein's theory of general relativity that's never been directly verified, but also to give us another tool to probe what's going on in the astrophysics of these neutron stars. So binary neutron stars, as the neutron stars orbit each other, they lose energy in the form of gravitational waves, and they spiral together faster and faster, emitting a characteristic chirp waveform. And my audio's not too good, but I'll try and play it for you. The chirp waveform they emit sounds very much like that ball bearing going down a plug hole. So this is a computer simulation of two binary neutron stars coalescing. For those of you who can't hear it, it starts low amplitude, low frequency, goes up to high amplitude, high frequency, goes whoop. They're the gravitational waves emitted by two binary neutron stars as they crash into each other and merge. Okay, so that's one of the sources we're looking for, binary neutron stars. The gravitational waves emitted by binary neutron stars. Another source we're looking for, which is a really cool source, is binary black holes. A black hole is what happens when a star, very, very heavy, massive star, exhausts its nuclear fuel, and the heat generated by the heat and pressure generated by its nuclear burning can no longer support the mass of the star. The star goes supernova, the remnant of the star collapses down, keeps on collapsing under gravity, nothing can stop that gravitational collapse, until the matter all disappears down this throat of space-time, and this black hole becomes pure space-time curvature. This picture shows, again, this blue sheet here is the surface of my trampoline. This throat here is the curvature in space-time caused by, I've drawn a little black hole above here, so you can see the black hole above here, and this is the gravitational wave emitted by two black holes going around each other. The other one's just up in the corner here, so let me start this going. So this is a movie, computer simulation, of what happens when two black holes orbit around each other. They emit gravitational waves. The two black holes go round and round each other. We fast forward a little bit. They go round and round and round until eventually they touch each other right here, and then they merge, and then they ring down like a big blob of jelly. So, forming a single black hole here is the throat of the final black hole. There's an awful lot of physics going on in that in-spiral emergence. This movie took about 30 years to make. Okay? This is the black holes are one of the most exotic predictions of Einstein's general relativity. They're manifestations of the strongest space-time curvatures you can get. Solving the Einstein equations and understanding the behavior of these black holes has taken people, well, almost as long as GR has been around. To do these numerical simulations of binaries, they started in the 60s, just trying to get a black hole to sit there on a computer and have the computer solve Einstein's equations. Trying to get that took about 20 years, and then trying to get black holes to collide took even longer. Trying to get a black hole to sit there took about 10 years. Trying to get black holes to collide took another 20 years ago. The Einstein equations are incredibly complicated, and simulating these merging black holes pushes computational physics and our mathematical understanding of GR, of the nature of gravity, to its limit. This movie, the source of this movie ran on a supercomputer. It took us about 3 months to run the simulation to actually figure out this gravitational waveform, just to watch the two black holes go whoop, plump, and fall into each other. Why do we go to all this effort? Well, because encoded in this waveform, encoded in this wiggling and wobbling here as the two black holes merge, are clues to the nature of gravity. Gravity is one of the 4 fundamental forces of the universe. It's the one we understand the least. Encoded in this gravitational wave, and in these wiggles, and in this merging black hole, is strong field gravity, clues to the nature of gravity, what's going on in the universe. That's one of the reasons we're going after gravitational waves, to understand one of the 4 fundamental forces in the universe in ways that have never been tested before. Okay, so about this time you're probably thinking, okay, so you've told me about gravitational waves, you've told me about black holes, you've told me about LIGO, what about some results? Have you actually seen anything or not? So let me preface my discussion of results with a slight caveat that LIGO people tend to do, which is it's really hard, right? This is not something that's easy. This is something that's been going on since Einstein. Einstein predicted gravitational waves in the first paper he wrote after his paper on GR, predicted the existence of gravitational waves. Then he wrote another paper with Rosen and said, oh, actually no, gravitational waves aren't real. And it took theorists about 40 years to argue backwards and forwards about whether or not gravitational waves even exist, or whether just some mathematical artifact of relativity. Observing the universe with gravitational waves is a tremendous challenge. The timeline for gravitational wave observatory starts way back in 1972, when Ray Weiss wrote down the design for a first-generation gravitational wave observatory. This is LIGO. LIGO was designed its baseline design was written down back in 1972. It wasn't until 1994 that we actually started building the LIGO facilities. There's a huge amount of work and time and effort to get from Ray's sketch of what one of these things should look like to actually building it. Then the construction took many years. The construction just to build the LIGO detectors from 94 till about 2002, when we could actually credibly turn on the detectors and say, yes, they really are now laser interferometers and they're taking astrophysical data, took another 8 years or so. This is 2002, when initial LIGO began its first science labs. What makes detecting gravitational waves so difficult today? Well, part of the problem is that noise limits our sensitivity. This is a simplified diagram of LIGO. This is the laser, here are the mirrors. We're trying to detect changes in the length of these arms. It's a little bit more complicated than what I showed earlier. But the strange signal that comes out, if LIGO was a perfect instrument, we'd just sit here and wait for a gravitational wave. But the problem is, inside this, coming out of the detected data here, is noise. These mirrors aren't perfectly isolated from the ground. They're in fact, they're slightly hotter than room temperature because they have a laser beam shining on them. They're hot, they're warm mirrors, they're hung from wires, they're not perfectly isolated from the ground. You can actually play some noise right now. You almost heard it. Never mind. So the noise, the environmental hiss of atoms jiggling around on the surface of this mirror, of seismic noise, which we try and suppress to our best as much as we can, coupling at these mirrors, making these mirrors move around in the way a gravitational wave makes them move around, causes noise in the mirrors. It causes this hiss. This constant hiss of noise from all these different sources in the detector. And the trick to detecting gravitational waves are beating these noise sources down to a level where you can actually hear that whoop in amongst all this hiss of noise. When you beat down the noise, what it translates to is being able to see further and further and further out into the universe. You see more of the universe, you're more likely to see these neutron stars crashing into each other. So how are we doing right now? Well, September 2002, this is where my timeline picked off, LIGO could basically detect gravitational waves in the Milky Way. The size of the scale of the Milky Way is about 50 kiloparsecs. This is artist's impression of our galaxy. Here's us with the sun, and here's the center of the galaxy. So when I first started doing observing rooms in LIGO, we could basically see the Milky Way. Then, March 2003, after we'd been beating on these noise sources for a year or so, we got sensitive enough to see Andromeda, the next nearest galaxy to the Earth. Then we beat on the detectors a bit more, trying to get as many of the noise sources down as we can. I can tell you about that separately, but that's a whole other talk. Beating the noise sources down, we can actually start to see out to clusters of galaxies, out to the Virgo cluster of galaxies. This is a cluster of galaxies out here, containing many galaxies the size of our galaxy and our nearest neighbor Andromeda. This is 20 megaparsecs. This is the design sensitivity of initial LIGO. This is what we promised we would do with initial LIGO. We'd build a detector that's sensitive enough to see out to the Virgo cluster of galaxies, see enough galaxies that maybe we might start to detect gravitational waves. We didn't promise to detect, we promise to build a detector capable of detecting. Subtle difference. So the results so far from the initial LIGO detectors, all the LIGO Virgo data up until October 20th, 2010, has been searched for binary neutron stars and black holes, and unfortunately we have no gravitational wave candidates. But that's not inconsistent with what we know about how far out of the universe we need to see to detect gravitational waves. We need to see a whole, black holes crashing into each other is not something that happens every day. It's not something that happens all the time in our galaxy. You need to see a whole lot of the universe to be able to see enough volume of the universe to see enough of, to see black holes colliding into each other. So we're pushing that sensitivity down. We did do one thing though, kind of masochistic thing actually in retrospect. In the data we took from the last 2 years of LIGO observations, we did something called a blind injection challenge. What we did, because we knew it was possible but not probable we'd detect something with initial LIGO detectors, we said, okay, we'll do a secret end-to-end test of our detection capability in LIGO and Virgo. What we'll do is we'll inject an in-spiral signal. We'll inject one of these in-spiral coalescence, these binary black hole, binary neutron star signals into the data, and only 3 people in the collaboration, there's about 800 people in LIGO and another 400 or so in Virgo, only 3 people in the collaboration knew that this signal was going in, where it would be in the data, if it would even go in at all. So Joe Giammi, Jay Marks, and Mike Landry, who basically masterminded the blind injection challenge, stuck a signal into the detectors by electronically moving the mirrors in the same way that a gravitational wave would move the mirrors. We saw it. We detected the signal that they put in. They put in the type of signal we would expect to see. A neutron star merging into a black hole. This is what it looked like in the Hanford Observatory. This is time and this is frequency. This is what this characteristic chirp looks like in a time-frequency plot, going whoop, whoop in the Livingston detector. We actually detected this signal. This caused a lot of excitement. This is why I'm late with Alice's paper. A loud candidate was found by the search. Loud candidate was found when we searched the detector data. We got very, very excited. The false alarm rate, the conservative false alarm rate, including all things like trial factors, was 1 in 7,000 years. We'd have to take 7,000 years worth of data with the LIGO detectors to see something as loud as this. And we wrote a paper on it. We wrote a full detection paper going through the whole rigmarole of all the analysis, end to end, doing everything. We had a 4-page PRL. This is the best paper I've ever written that will never be published. We had a 4-page PRL that we prepared for submission to physical review letters announcing the first detection of gravitational waves. And then they told us it was an injection. And then Alan, who's the co-chair of our group, got out a bottle of whiskey, put it on the table, and then the meeting was pretty much over. So we, even though we haven't actually detected signals, the universe hasn't played nice with us so far, we haven't actually detected signals yet, we have gone through this end-to-end challenge of, we know that the instruments work, we know that our analysis works, we know that the sociology of our collaboration works, we can actually get to a point where we can claim a detection. And so, we've done this end-to-end test, and so we're confident if we can just get those noise sources down to a level where we can see far enough out into the universe, that we see enough of the universe that we can really start detecting binary black holes, we can start observing the universe with gravitational waves. Let me conclude with what's going on now. Well, initial LIGO, the first generation detectors, was so successful, we pulled them to pieces. So this is the state of initial LIGO as of a few months ago. This is the steel beam tube I saying that's inside the concrete beam tube. This is the data acquisition and control systems. This is the stuff that used to be in here. This used to be a control system, one of the interferometers. Now it's just an empty VME crate with not much in it. This is one of the mirrors from the detector. This is one of initial LIGO's mirrors. This is the mirror that the laser beam hits at the end of the 4-kilometer tunnel and comes back. This is someone's hand to give you a sense of scale. we're pulling the initial LIGO detectors to bits. Why is that? Well, we're preparing for Advanced LIGO and Virgo. These are the detectors that we really want to build. These are the detectors that are actually going to be sensitive enough to detect gravitational waves and open a new field of astronomy. We demonstrated the technologies of initial LIGO, now we're doing it for real at a sensitivity where we can detect gravitational waves. This is one of the advanced LIGO mirrors that's being prepared to go into the LIGO system. We're basically ripping everything apart from the vacuum out of initial LIGO, putting in a whole new set of optics, more powerful lasers, better suspensions, all to beat these noise sources down and increase our astrophysical reach. In this picture here, each one of these dots is a galaxy. They're not stars. Each one of these dots is a galaxy. And these are superclusters of galaxies. This is the range of initial LIGO, the detectors that we started observing the universe with back in 2002, and reached basically this sensitivity. Here's the Virgo supercluster just here, just inside the reach of initial LIGO. Advanced LIGO will be 10 times more sensitive than initial LIGO. It will see 1,000 times, 10 cubed, the volume of the universe, 1,000 times more galaxies, and actually be able to get to a sensitivity out here. Binary neutron stars are coalescing 40 times a day. So 40 times a year, which we're coalescing 40 times a day. We're coalescing 40 times a day, I've been announcing a detection right now. Out here, if you can see out here, you may expect about 40 binary neutron stars coalescences per year. There may be many tens or even hundreds of binary black hole coalescences out here. We don't know because we don't have as much, we've never seen binary black hole coalescences directly, so we don't have much to handle on those. But Advanced LIGO and Virgo are the window that will open a new window on the universe. Factor of 10 in amplitude sensitivity, which translates to a factor of 1,000 in rate. 1 day of Advanced LIGO is worth more than a year of initial LIGO data, given the increase in sensitivity. They're fully funded by the National Science Foundation and are under construction right now. I showed you a picture of one of the Advanced LIGO mirrors going in. And we expect we're going to have another process of getting them installed, beating down the noise. We expect the first science observations to come in 2015. This is really nice because the students who are starting grad school now, or undergrads, particularly undergrads, who are working on undergraduate research in LIGO, you can look them in the eye with a straight face and say, you're going to see something, right? Unless we fundamentally misunderstand something about the universe, or we screw something up horrendously building advanced LIGO detectors, we are going to detect gravitational waves. And you are going to be the first students who are going to look at the universe in a completely new way. That's really exciting. So let me conclude. So, first generation gravitational wave detectors are kind of like, the first optics that people built, the first glasses that people built. Proof of principle demonstrating that we can do it. We can focus light. We can build a detector capable of detecting these tiny, tiny displacement sensitivities. Advanced LIGO is kind of like Galileo's first telescope. It's the first time we can actually really probe the universe in a new way. It will see things we've never seen before. There's no way to observe the things that Advanced LIGO will see. It will open a completely new window on the universe. What people are even thinking about right now is where we go after this. What's the Hubble of gravitational wave detectors? People are beginning to think about perhaps third generation underground detectors that might observe the whole universe in gravitational waves. Third generation detectors. People are thinking seriously about this. And people are putting real money into this. This is how confident we are about the success of Advanced LIGO and the new window that it will open on the universe. Okay, thanks very much.
Well, thank you very much for sharing some of this excitement in the future. That's great. I'm going to be happy to answer some questions. That's great.
When a gravitational wave passes through matter, is there appreciable absorption or refraction?
So, no, and that's actually a really good... Oh, sorry, so the question was if a gravitational wave propagates through matter, is there appreciable absorption of the gravitational wave? The answer is no, because gravity and matter couple so weakly. And that's actually really good. If we can build the instrument sensitive enough to detect gravitational waves, that's actually a really good thing, because it means we can probe into regions of the universe that you can't observe electromagnetically because they're obscured by dust, by stars, by other things. Or the source of the holy grail in a way is observing back. As you look out of the universe, you're looking back in time. The furthest back you can look is the surface of our scattering, the cosmic microwave background, at which point the universe basically became opaque to electromagnetic waves. So you can't see back in time further than that surface of our scattering, unless you're observing gravitational waves. Because gravitational waves will go through that thick soup of the early universe, not being scattered, not being absorbed or refracted in any appreciable way, and allow you to see back to the first, the Planck time, and when gravity became unified with the other forces, and we can probe the early universe. So this is another reason why they're exciting source. They can probe regions of the universe in ways that electromagnetic waves can't.
Great. Two quick questions, if I may. You know those stochastic sources from the Big Bang that you mentioned? What would the source distribution in the sky look like?
So that would basically be it would be at first order an isotropic distribution, right? So if you think about the cosmic microwave background, when the cosmic microwave background was first discovered in electromagnetic waves, first order it's isotropic, right? Whatever direction you look, you hear this hiss. Same with gravitational waves. Whatever direction you look, you hear this hiss. Perhaps, if we could detect it, we could study it like you do for cosmic microwave background and see,
variation.
Exactly, multipolar structure in the gravitational wave cosmic microwave background, which will give you more information about the early universe.
Okay. The other question is, so for your coalescing binary star signal, with Advanced LIGO, will it last longer because you'll be sensitive to it earlier?
Yes. So one thing I didn't say is the frequency band of the LIGO detectors. So the great thing about LIGO is we're detecting gravitational waves in the audio frequency. You can literally plug a pair of headphones into the back end of the LIGO detector, and you can listen to the noise and maybe one day the gravitational waves coming out of LIGO. The initial LIGO detectors are sensitive to gravitational waves between about 40 hertz and about 1.5 kilohertz. So the audio band, basically. The low frequency sensitivity is limited by seismic waves. The low frequency seismic waves coupling in and causing the mirrors to jiggle quite a bit at low frequencies. Advanced LIGO, because we'll have better seismic isolation, can see down to 10 hertz. And so you can actually see you're pushing down the overall amplitude sensitivity, you're also widening the band. So you see these binding neutron stars they've been doing their thing for billions of years. We see the last 25 seconds in initial LIGO. In Advanced LIGO, we see the last hundreds of seconds, about 200 seconds. And so, you're seeing the last 200 seconds, and probably the most exciting 200 seconds of two stars have been evolving together for billions of years.
Yeah, he may have asked it already, and I didn't understand the answer, but why didn't you start out with a multi-axis like the underground system that you showed last, in every direction possible, and more directions, and more likelihood you can cross compare for
the short answer is the National Science Foundation's pockets are only so deep. I mean, if we could have gone straight to a third generation underground gravitational wave detector, it would have been awesome.
I think it's also there's a lot of technology.
A lot of technology needs to be developed. I mean, the roadmap. I mean, I illustrated from the roadmap. We couldn't get to Advanced LIGO without going through the 40-meter prototype, without going through initial LIGO, without going through, and we won't get to third generation without going through Advanced LIGO. Even though we're starting to think about third generation now, there are things, and we should be doing 3G research right now, there are things we're going to learn from second generation detectors that are going to inform us for third generation detectors. So while it'd be great to hop to the end goal, we need to get through development, we need to build up gradually and prove our worth to the funding agencies as well, that we can actually achieve what we say we're going to achieve.
You mentioned eliminating noise through seismic isolation. What other things are you doing in Advanced LIGO to reduce noise? Just
So there are, I don't want to get, like I say, I don't want to get too technical, but the three fundamental noise, there's three fundamental noise sources in LIGO. Seismic at low frequencies, thermal noise in the kind of intermediate frequency band. The thermal noise is basically, we're trying to detect these 10 to the minus 20 meter displacements. That's smaller than a proton, right? We can see the atoms jiggling on the surface of the mirror. So you can see the atoms jiggling on the surface of the mirror due to just Brownian motion of thermal noise, and then this thermal noise from the suspensions. At high frequencies, this photon shock noise, which is a quantum mechanical effect of how we actually read out the photons of the photodetector. What we're doing in Advanced LIGO to beat down the sensitivity is better seismic isolation. We actually have something called HEPI, which is the hydraulic external pre-isolator. It's better active seismic isolation that pre-isolates the stage that the mirrors are on. And then inside, so there's better pre-isolation outside. That helps us really beat down the lowest frequencies. Then inside, we have the isolation for LIGO is actually pretty simple. It's a standard. It's blocks and springs and blocks and springs. And every time you get a mass in a spring, you get a certain amount of isolation. So we have big masses and stiff springs, and we have chains of these and we isolate them. We're doing a better job of that passive isolation inside. Bigger mirrors, so heavier pendula, and so that's beating down the low frequency sensitivity. The bigger mirrors also gives a bigger spot size. We get better averaging of the thermal noise. That beats down the thermal noise. Better coatings, more powerful lasers. There's a laundry list of technologies, but that's basically that's the essential. So external pre-isolation, better passive isolation inside the stacks, more powerful lasers, bigger mirrors, and a ton of other, a laundry list of other things.
Great talk, thanks, Duncan. When you showed the change in the observing area for preliminary LIGO as opposed to the advanced LIGO, and we talked about how you kind of go to a factor of 1,000 larger, if you will, in volume. But since you're looking so much further back in time, you're looking at the objects earlier in their existence. And since you're waiting till the end of their events, if you're talking about these crashing together black holes, you don't necessarily have an increase in the same number of events.
We're actually we're actually not looking that far out in terms of cosmological distances. So we're not looking out to so initial LIGO is not looking out to really high redshifts where you have to worry about cosmological effects. This distance here is about 20 megaparsecs. This is about 200 megaparsecs. So it's not you're not Z of 5. But as you go out, there are earlier generations of stars. I mean, one of the things we want to do with third generation detectors, when we build them, is see the population of 3 stars. So the first generations of stars that lived in the universe. We know very little about these first generations of stars that lived and died in the universe. The progenitor stars for the stars that we see today, stars like our sun. Our sun's not one of the first stars to form in the universe. We know that because it has metals in that were formed in earlier generations of stars. But if we can see out to high redshifts in gravitational waves, we can see these earlier generations of stars coalescing. But for an advanced initial LIGO, you're not seeing so far out that you have to worry about cosmological effects just yet.
Jordan, do you get the noise so that the signal actually, do you have to pick the signal out of the noise, or is the noise ever going to be lower than the actual signal? You have to pick,
so unless we get really lucky, in advanced LIGO, you have to pick the signal out of the noise.
So you have to have some idea of what it might look like.
Right. So you have to. So you have to. There are 2 main approaches. When you know what the signal looks like, you can do the optimal search. You can match filter for the signal. You have a template, and that's why all this effort went into generating these binary black hole waveforms, to give you a template for what you were looking for, because you know much more sensitive search. But if you don't have an accurate template, maybe for supernova or just things you don't know about, you can use time frequency methods to try and extract the signal from the noise, but you lose sensitivity by doing that. So for binary neutron stars, binary black holes, we'll probably be dragging the signal out of the noise. There should be a few loud signals, but the first signals we'll be seeing will be pulling the signals out of the noise with signal processing techniques, and that's where a lot of the effort in LIGO goes, which is develop these signal processing techniques that we're never going to beat the noise down to a level where, at least in we will in third generation detectors, but in Advanced LIGO we won't get the noise so low that every signal will be above the background. But there'll be some loud sources that will just stick up. Unlike LISA, the planned space-based detector where all the signals are just way above the noise. But that's a whole other story.
Yes.
Did ever any condensed matter physicist approach you asking for the noise data to maybe potentially learn something about lattice dynamics?
Sorry, say that again?
Did condensed matter physics approach you asking for your noise data to potentially learn something about lattice dynamics?
No, they haven't. So at the moment, we're kind of keeping something of a lid on the LIGO data because our field has something of a history of fault detections and going back to Joe Weber and claims of gravitational waves that turned out to be false. And so at the moment, we're kind of keeping the data close to our chest to make sure that any claim of gravitational wave detections is really, really, really strong and not affected by biases or anything like this. And when we detect, we'll put the data out there.
He was asking a different question.
Oh.
He was asking, could you learn some solid-state physics from the behavior of the mirrors?
Yes. Oh, sorry. Yes. You actually. Yeah. You can learn about the. In fact, Peter Solson's lab in Syracuse. They look at the solid-state behavior of the mirrors. I don't know if lattice people have talked to us, but certainly there's a lot of solid-state physics on the laser development side as well that goes into the development of Advanced LIGO. That's a little bit out of my field, so I can't say too much about that. More on the astrophysics and the analysis side.
Right. Any question?
Yeah, at the beginning of your talk, I think you mentioned that gravitational waves propagate at the speed of light. Is there an obvious reason why that's the case?
So, the question is, I claim that gravitational waves propagate at the speed of light. Is there an obvious reason why that's true? The answer is yes and no. It's possible that gravitational waves don't travel at the speed of light. That's if Einstein isn't quite right, then it's possible that gravitational waves might not travel at the speed of light. If you do the calculation in Einstein's theory of general relativity, like you do if you have Maxwell's equations that describe the electromagnetic field, you can try and figure out from Maxwell's equations how fast electromagnetic waves will travel. And it turns out that the speed of propagation is the speed of light. We've experimentally verified that. You can do an analogous calculation in general relativity that says, okay, give me the wave solutions for general relativity, and you can read out of those theoretical equations a prediction for how fast gravitational waves should travel. And that's not an obvious calculation I can do off the top of my head, at least with a whiteboard, but you can do that calculation. It predicts they travel at the speed of light. That also predicts that the graviton, the equivalent of the photon, is massless. It's possible that one of the things we want to test is the nature of gravity. Is the graviton really massless? If the graviton is not massless, then gravitational waves wouldn't propagate at the speed of light. And if we can do coincident measurements of gravitational electromagnetic sources, we can test the speed of propagation of gravitational waves. That's a hard problem, but something people want to do because it would help probe the nature of gravity to try and measure experimentally the speed of propagation of gravitational waves and say, does it match Einstein's theory?
I think we have time for one more question.
You used the LIGO and the other one, a handful, right? How many detections do you make before you eliminate false detections by coincidence between the two?
We always require coincidence between the detectors. We don't even consider the possibility of detecting a gravitational wave in a single detector because we want to be really, really sure we detect gravitational waves. The wave, we actually, one of the problems with being sure you detect, this is actually a very deep question. You want to be sure you've detected gravitational waves, right? You don't want to come along and say we detected gravitational waves and you haven't. It's not like you can't hold a photographic plate up and say, here's a picture of the star exploding. You need to be able to claim the detection of gravitational waves, especially if they're buried in the noise. What we do is, and you can't turn off the sources of gravitational waves. High-energy physicists at CERN, they're looking for particle decays in their detector, and they want to measure what we call the background rate, the false alarms in their detectors. They can turn off their beam. They can just turn off the beam, and they can see how many triggers they get from cosmic rays and all these background sources from radioactive decay and material in the detector, etc., etc. We can't turn off the universe is gravitational waves. We can't stop all these black holes coalescing to measure the noise background rate in our detector. That's one of the key reasons why we built two detectors. What we do is we know that gravitational waves propagate at or near the speed of light. And so gravitational waves should be no more than 10 milliseconds, which is the light travel time between Hampton and Livingston, separated by no more than 10 milliseconds between the two detectors. So what we can do is we can actually shift the data from our detectors by 10 seconds, 20 seconds, 30 seconds, 40 seconds, rerun our analysis, and look for how many things are coincident between the detectors by accident. Right? And that gives a handle on our background rate, the accidental rate of coincidences. Then we can line the data back up again, and we can say, okay, now how many more things do we get coincident? And that excess of things in the coincident data above these what we call time slides in the background, that gives us our rate of gravitational waves in the data. That's one of the key methods we use to do the analysis. So it's critical that we see the signal in both detectors because it comes in how we detect, how we measure the background, etc., etc.
Let's all thank Duncan again.